Hi, Reed.
Hey Brendan, how's it going?
Not too bad. I'm just gonna wait a couple more minutes to see if anyone joins.
I'm good.
All right, I'm gonna go ahead and get started. So I'm going over surface pressure distributions in hypersonic flow fields, otherwise known as local inclination methods. So we're going over a few different methods today: the Newtonian method, the modified Newtonian method, tangent wedge method, the tangent cone method, and shock expansion method. And we're also going to go over what pressure distributions in separated regions and reacting flows look like. Those are a little different, but let's just dive right in. So I'm assuming you have a working knowledge of the fluids governing equations, continuity, conservation of momentum, energy, species, that kind of stuff. And I'm also assuming you're familiar with the compressible flow relations, specifically the isotropic relations, oblique shocks, Prandtl-Meyer, and Taylor-McCall equations. So this first method, it's kind of neat because Newton came up with it for low speed flows, and he was completely wrong. But essentially, he was accidentally right for hypersonic flows, which is kind of interesting. But as seen on the previous slide right here, the fluid particle loses all of its normal momentum and conserves its tangential momentum. So using that fact, we can get some equations out of this. You can get the equation for the normal velocity, the mass flux blocked by the surface, and then the momentum lost per unit time. And then if you take this momentum loss per unit time and say that's equivalent to your force, and then move the area from to the other side, you can say that that's your pressure distribution sort of. And then from there, you could take it further and get your pressure coefficient distribution as well, and you get this CP equals 2 sine squared theta, which is why it's called the sine squared law. And then when you have those, you can also calculate your all your other coefficients, your CDCL and your lift drag ratio from this, and also the regular expressions for CDCL. And yeah, so the major takeaways from this one is that when the theta decreases, your lift drag ratio increases, and it becomes infinite at theta equals 0. And this makes sense because this is for inviscid flows. So skin friction, drag, and shear are ignored. Your CL increases as theta increases, but there's a maximum at theta equals 55 degrees. And then at theta is less than 15 degrees, your CL variation is nonlinear, which is unlikely for subsonic and supersonic flows, but more likely for hypersonic. And then using the Newtonian method here, you can calculate your drag coefficients on some of your basic shapes. The sphere is the CD is 1 and the CL is 0. The cylinder, the CD is 4/3, and the cylinder is also 0. And another interesting thing is that these are independent of Mach number. You can look through the notes and see that there's this concept of independence of Mach number, and they go through about how some of this stuff is independent of Mach number. And then there's a modified Newtonian technique where they essentially look at stagnation points and calculate the pressure coefficient that way, and then they relate that to the isentropic relations to get it in terms of Mach number and gamma. So you can calculate your pressure coefficient at the stagnation point based on your free stream values and the pressure at stagnation point as well. I got tired of writing in text, so you're going to have to deal with a little bit of my handwriting here because I had already written it down. But you can use the oblique shock relations, and replacing the subscript 1 with infinity, you can derive these equations for your pressure and your pressure coefficients. They're long, but there's online calculators you can use. You could write your own calculator to do all this stuff too. So, and then from there, you can plug in the relation that we started with, which was your pressure coefficient at the stagnation point, and times sine squared theta, and you can get a CP in terms of only, again, and this shows the independence of Mach number thing again. So you get a CP only in terms of gamma and theta. And then so you can treat this whole thing right here as just a coefficient A, where when your gamma approaches 1, your A approaches 2. And when Mach numbers become sufficiently large, your gamma does approach 1 anyway. So this being your specific heat ratio of just, normal air, and then this being increasing Mach number specific heat ratio. And then, so this method holds well for blunt bodies because it predicts the exact pressure at stagnation points, and that's useful. So this method is, I think, even more interesting. It's the tangent wedge method. You can sort of see an outline of what it does here, but it's suitable for sharp-nosed bodies that have attached shocks and are at sufficiently high Mach numbers. But so in this one, you're sort of iteratively solving for the pressure distribution around the sharp-nosed body. And you're assuming that each point along the body can be locally replaced by a tangent wedge. And I'll go over what a tangent wedge means. The first method would be you draw a tangent line at the nose of the sharp nose right here. So you would draw like right here. And then you would find the angle between that tangent line and the free stream vector. And then you can use those two things to calculate the oblique shock angle using your oblique shock relations. And then you need to check if that calculated shock angle is within reason, meaning if it's less than the maximum angle at that particular free stream Mach number. And once you've checked to make sure that's true, you can select any point on the surface and then draw a tangent line at point I. So right here, they picked this point as point I. They drew a tangent line there. And then they've essentially locally replaced this point with a wedge that has this angle as its wedge angle. And then from there, you can calculate your pressure at point I from the known wedge angle and Mach number, again, using your oblique shock relations. And you can do that for every point on the body. So, and that gets you a pressure distribution along the entire sharp-nosed object. It's important to mention that, this is only for 2D surfaces, and that's why we also have the tangent cone method, where you do the same sort of thing, except instead of replacing it with a tangent wedge, you're replacing it with a tangent cone. And the tangent cone is a little more tricky to solve for. You have to solve the Taylor-McCall equation to get the shock angle for the given cone angle. But yeah, the given cone angle is the same angle you get from drawing that tangent line at the different points. But you have to solve this whole thing to get that. It can be done, but it's not easy. And then we have the shock and expansion method. Essentially, this one uses the Prandtl-Meyer relations instead of the oblique shock relations. and it's valid for attached shock conditions as well. What you would do is you would calculate the flow deflection angle at the nose. So then we're going to call that theta n. And that's the same thing as the wedge angle at the nose. And then you can calculate the Mach number and pressure at the nose using the oblique shock relations with the known wedge angle and the Mach infinity. And then from there, you can use the Prandtl-Meyer relations to predict any Mach number at any other point on the surface. And you do that by, select a point downstream of the nose and calculate theta I using a tangent line. So right here, they drew this tangent line at I and calculated theta I. And then you can assume expanding flow between the nose and that selected point. And then from there, you can subtract the two, you get Prandtl-Meyer relations for each theta, and then subtract them to get your solve for this equation here for the MI, and then you get your MI. So then you can use MI for every point on the flow field, or rather you can use MI to calculate the rest of the flow properties using isentropic relations, which is, isentropic relations are a lot easier. You don't have to go calculating something insane for every point on the nose. And then you can also apply this to axisymmetric problems. You would replace the deflection angle theta with the semi-apex angle of a cone. I need to brush up on my geometry. I'm not sure what this is, but you can do it. Whoops. And then separated regions, these are a little different. You can see over here that this is just the supersonic flow over just a wedge. And then right here, you have a locally separated region circled in red. It's unfortunately, there's no nice analytical way to calculate these. You have to use computational Navier-Stokes space solvers to do it. But from the picture on the last slide, we can see the locally separated region causes two more shocks to form. We have the induced separation shock wave and the reattachment shock wave, and that definitely affects the pressure distributions along here. And this is from the high speed gas dynamics book that we have by Anderson. So they've graphed the pressure distribution inside of that locally separated area to find that the pressure kind of increased at first, and then toward the center of that locally separated area, it plateaued a little bit. And then as it reached the reattachment shock, it started increasing again. And reacting flows, again, no nice analytical way to solve this. You have to use Navier-Stokes installers. But this time, instead of just using the momentum and continuity equations, you're adding the energy and species conservation equations as well. And then the graph shown is the pressure distribution about a hyperboloid, also from Anderson's book on high temperature gas dynamics. And then you have, these there are different types of reacting flows. You have your non-equilibrium reactions, your equilibrium reactions, and then just the Newtonian regular flow. But yeah, that's sort of everything I have on pressure distributions. Are there any questions on any of this stuff? I know it may have been a while since we've all taken compressible flow, or rather high speed aero. So some of these relations were a little hard to remember, but once you see them, it kind of jogs your memory. Alrighty. Well, that's all I had. I don't know who was presenting next and if they're going to be here.